All right, it's 1:35, so we'll get started. So any questions from the last lecture? So where we're at is we finished up all of the powder processes, and you can take a look at this diagram right here. And now we're starting to talk more about these liquid-based processes. So this generally falls under chemical reaction bonding, and we'll talk about that today. But now we're getting into the printing technologies that are going to use liquids without a powder bed. So multi-jet fusion and high-speed sintering, of course, use liquids in order to solidify these powders. And we'll talk a little bit more about binder jetting, and we'll compare and contrast the inks that are used. But now we're getting into more printing with liquid polymers and the technologies like polyjet and SLA that incorporate these types of feedstocks. So we're going to talk about inks today. We're going to talk a little bit about binder jetting because some of those inks are interesting to think about. And then we'll move on to polyjet. And then finally, we'll get into stereolithography either next lesson or in a week from now. So I did find one other really nice polyjet video, and so I'm going to share that with you because I think it really describes exactly what we're looking at, and they talk about how parts are built up. And so I want to make sure that everyone's on the same page in terms of how this process works. So let's watch this video so everyone can get oriented to what we're talking about, and we'll go back and forth a little bit between what's going on with polyjet versus binder jetting today and how those inks are set up and some of the interesting issues around them. So let's check out this video. The link is on the slide, but let's see what they have to say.
To take what's in your imagination and put it in your hands. It's pure magic.
It seems so out of this world.
You know, this can put manufacturing in a lot more people's hands.
Polyjet is amazing because of the type of quality that you get. You get really high definition, you get great surface resolutions, and you can have multiple parts in your hands within hours. It's the fastest technology that we offer.
Polyjet really shines with its surface finish and its ability to resolve very fine features.
The polyjet process extrudes out or jets out a liquid resin that can be cured with a UV light.
They are made to react to ultraviolet light. And so that's the catalyst that causes these two separate components to come together to form the third, solid plastic component.
So with the polyjet system, it jets out a thin layer of the photopolymer resin. It cures it with the UV light and then builds a cross-section of that part layer by layer.
So after one cross-section is deposited, the platform will drop down, allowing the gantry to pass with layer number 2, and then every subsequent layer after that. When the part has completed building, we will remove it from the platform.
So the parts coming off of this technology are really smooth. They don't require as much hand finishing and post finishing after, and they can create parts with really, really good looking detail.
We do paint ready, we do very custom detailed work, so if you're looking for that amazing showpiece for a trade show, that's something that we can definitely accomplish in-house.
They say a picture's worth 1,000 words, a part's worth 1,000 pictures.
What we can do with Polyjet, there's just such a wide range in materials. We're printing hard plastics, and we're printing soft shore material, and we're able to make overmold pieces now where you're combining the two materials.
So like a drill that has a hard substrate and a rubber grip, you can build that in one piece.
You know, as Stratus is direct manufacturing, having the engineering talent on our end to work with the engineering talent on the customer's end is real exciting because that's where the good stuff happens.
You get to be a part of someone's idea and then make that a reality.
And if we put those tools in their hands, we don't know what they're going to come up with. And that is just awesome to, I can't wait to just kind of sit back and watch what's going to happen out of that.
Okay, so that's just to get everyone oriented again as to what PolyJet is all about. And they covered some key details in terms of the photopolymer inks, how they're jetted down layer by layer, and how they're UV polymerized to build up a part that's completely photopolymer, as shown on the right here, as opposed to what we've been talking about thus far with HP jet fusion and high-speed sintering, where you have both the ink and the powder working together. So that's just to get everyone set. And we've looked at some really interesting parts that can be made using this type of technology. So this is an Objet branded machine right here. They're also called Connex machines. So
I have a quick question,
Oh.
sorry, about the process.
Go ahead.
So after the UV lamp passes, like, is it completely cured? So you said like it's the mini droplets that are deposited, and then the UV lamp goes almost immediately after this has been deposited. Are they completely cured at that stage?
That's right. So they are almost 100% cured right during that first pass, because the droplets are small and this is at room temperature and the light is pretty bright. And so these types of polymers are meant to cure immediately, and there's usually not a lot of post finishing. So there's no post UV curing. It's not like SLA where sometimes you have to wash and cure the part after it's printed. And so these are almost ready to go right out of the printer. Now there might be some painting or some surface finishing or some sanding or things like that, but most of these parts are not post UV cured. Now, they're not 100% cured because they do have to stick together layer by layer. So there's some residual chemistry that allows the layers to stick together. And that's not well studied because this is a proprietary process. It's proprietary inks. And so there isn't a lot of research on PolyJet other than doing engineering parts, making engineering models, things like that. So there's not as much research into the process, but yeah, these are almost all cured right out of the machine. So I show this picture because it's showing the deposition head with the light right behind it. And you saw in that video, which is a real-time video, the light comes on layer by layer immediately to mostly cure the droplets in place.
Okay, thank you.
Now, the layers are very thin, and so it does take a while to build up these parts. And so the layers can be between 20 and 50 microns thin, and so you need lots and lots and lots of drops to build up the part. So it's like an inkjet printer, only in 3 dimensions. It takes a while, and so one of the problems with PolyJet is that they can be pretty slow, but you can get one of these models right out of the printer as is, ready to go. And so for prototypes, for demonstration pieces, this is high-end technology that's in use for a lot of that type of activity. Engineering resins are a little bit different matter. They don't have as high a strength because they're photopolymers. They don't have as much toughness because they're highly cross-linked. And so that's an issue getting the properties that you might like. But these parts would be really hard to make otherwise, or they'd be multi-part assemblies that have to be glued together or have to be assembled after they're printed, whereas PolyJet can print these parts as is. Good discussion. Any other questions on this? Okay, and so there's a lot of technology in terms of how to turn a design idea into what can be printed. And we talked a little bit about this last time in terms of dithering and how dithering patterns are achieved, or something like half-toning. And so this is getting into the idea that you can only build a part out of discrete droplets, like in this newsprint halftone on the right-hand side of the slide. Those are just black and white droplets of different sizes, whereas in the grayscale photograph, you have pixels with different gray values, which is a mixture of white and black together in the same space. And so all of these polyjet parts, in essence, are dithered or half-toned in order to get different colors or different properties out of the polymers, because it can only deposit a droplet of hard material and a droplet of soft material. It can't mix the hard and soft materials at the droplet level. So the droplets that come down out of the print head are either one type of material or the other type of material. And the software in these printers does the half-toning or the dithering in order to get the desired properties. So if you're interested in this sort of multi-material or mixing materials to get the properties that you want, we have classes on software for additive and other things like that, or you can dig into this a little bit more. This is not a software class per se, but I wanted to make you aware of it and let you know that there's tools out there, usually embedded in the printer, in order to do this automatically for you. And we'll talk about that in a couple slides. And so, for instance, we saw in the video that they had this idea of overmolding, where you might have a hard material and a soft material that's integrated together, just like if you have a plastic toothbrush with a soft touch grip on it, or sometimes your iPhone case will have little rubber grippers on it in a hard case. Those are what's called overmolded assemblies, where they injection mold the hard plastic and then overmold by injection molding or compression molding the rubbery bits onto that hard plastic. Whereas with PolyJet, you can make overmolded assemblies and mix these materials within the same print. And so there's a lot of different materials out there, and you can look on the Stratasys website. And so here's one material, it's called Vero White. So this is a hard plastic. And this is still UV cured. And so you see the nominal stress is relatively high, and it's got this yielding behavior, which tells us that it's hard plastic, versus this Tango Plus matrix. This is an elastomer that's soft, but this is a UV cured PolyJet resin. And there's a bunch of different spec sheets and material data sheets on this on the Stratasys website, or this data was taken from this SFF symposium paper. But now these two different mechanical properties can be integrated into assemblies that look like this. So you can have soft buttons in a hard case. Or if you want to make a tire, you can have different durometer rubbery materials on a hard wheel and hub. You can have, this is overmolding right here. So this is soft touch overmolding. Or you can have clear parts integrated with colored parts in this cutaway, what have you. And so this PolyJet process allows parts like this to come right out of the printer. And that's very exciting because you can get prototypes that are ready to go rather than having to assemble these these parts after they're printed like we would do in a conventional manufacturing process. Any questions about that? Okay, I suggest you take a look at what's out there in terms of PolyJet and all the different demonstrations that have been done. They're really awesome machines. They are expensive because it's proprietary UV photopolymer. And of course, these are big inkjet machines with big print heads on them, but the parts that come out are really spectacular. One of the things that PolyJet has been used a lot for, and that additive manufacturing has been used a lot for, is this idea of making manufacturing tools for another process. So this is thermoforming. And thermoforming is used to make lots of different plastic components. So this is a 3D printed form. And then this is a thermoformed component. And so if you don't know what thermoforming is, I have a couple of links in the next few slides. You can check it out on YouTube on your own. But thermoforming is basically you take a flat plastic sheet and you press it down on the mold. You heat it up and press it down on the mold, and then vacuum all the air out, and the plastic sheet thermoforms to the mold. And so you can make lots of these 2D or 2.5D components using this thermoforming technique. And so the ability to make molds quickly and to make high resolution molds isn't it one of the big advantages of this PolyJet process. So here's the basic thermoforming process. And so you have some sort of mold that's in the shape that you want. So the mold is 3D printed. And of course, it can be machined or whatever else you want. And then you put in your plastic sheet of choice. You heat it up a little bit, and then you pull the plastic sheet down into the shape that you want. In this case, this is a Darth Vader mask. So if you're in the Halloween mask business, that's how Halloween masks are made, or other sorts of plastic containers. Food packaging, a lot of food packaging is thermoformed. Like if you buy washed spinach at the store or something like that, it comes in that plastic, that clear plastic container. Those are thermoformed. And so thermoforming is used to make a lot of components, and being able to change the mold design is very useful when you're prototyping products, because making the mold is often the slow step in terms of design and iterations, and the molds can be expensive. And we'll talk about that in terms of injection molding in a little bit. But as you look at PolyJet processes, a lot of different PolyJet processes are used for thermoforming. So here are some links right here, and thermoforming is not that exciting. It's basically just flat plastic being turned into textured plastic. And so we won't watch a video on that, but there are some links if you want to check it out. So thermoforming is important, but we've talked about injection molding in the past, and how the extrusion part of injection molding is a lot different than what we saw with material extrusion AM with the heated liquefier. But this mold right here is where the part is shaped, and molds are usually steel and expensive and slow to make. So if you want to change the design on your sunglasses, or change the design of your iPhone case, or change the design of whatever plastic thing you're making, you have to have your mold re-machined, which means you need to take it to the machine shop. They can't add steel very easily. And so you can only take steel away, which is an issue. If you want to make a dimension smaller, you sometimes have to make a new mold, and that's really expensive. And so the injection molding industry would really like to have a fast way to prototype molds until they get exactly the right mold that they want, and then they can make it in steel for runs of tens of thousands of parts. But oftentimes injection molding is held up because you're waiting for the mold to be machined. And of course, injection molding is a huge industry. There's tens of thousands or hundreds of thousands of injection molding machines out there. Injection molding factories look like this. So these folks are cranking out toothbrushes or cranking out plastic dishes or what have you, bottles, plastic bottles, whatever their business is. There's a lot of injection molding going on. And so it's big business if you can innovate in terms of new mold designs. I think we've seen this video before, so I won't play it again, but you can check out injection molding. And so we're talking about how do you design and build this mold quickly. And so we'll see a case study where they're using PolyJet to do this. And so injection molds just look like this. So you can take a little gander at this if you want. And I think this mold, they're making toothbrushes. And so they're doing 16 toothbrushes at a time in a 4-cavity mold. And that's really interesting, but this is an expensive operation. And so there's a really nice application note right here from Stratasys on how to use PolyJet prints to make shapes for these molds. And so this is a PolyJet printed mold of whatever shape you want inside a steel cavity that holds the pressure and everything else. So we're going to watch this video, and they're going to explain how they develop molds using PolyJet for injection molding operations and how that helps them on cycle time, speeding up design and speeding up iteration. So let me see if I have this video queued up. Let me switch over here. There we go. All right, yeah, this is the right video. So we'll check this out.
My name is Mike Ellis. I'm the Global Director of Marketing Communications for Millicron, located here in Georgetown, Ontario. 3D printing has been part of our industry for a number of years now. Customers have been using it for a variety of different methods, and it's becoming a lot more prevalent over the last, I would say, 2 years. The Millicron Group has been focused on expanding our innovative portfolio, and 3D printing technology just goes with our injection molding machines quite nicely. Prototyping is huge, so whenever one of our customers comes out with a new product, they need to test it, they need to test market it, and they need to make sure that it's functional for their customers. And to do that, they typically do low-run production jobs. They also have minimal designs for their molds. Typically, these mold cavities can take weeks to manufacture. So with 3D printing, if we can actually print the mold cavity and use them for prototype jobs, that can allow our customers to get their prototypes into the market faster, thus approving their products for final release and high volume production. For us, speed to market is critical. So anything that we can do to help our customers get their products faster to market, it helps them, it helps us.
My name is Witold Netter. I work for Moldmaster. I'm responsible for technology development and supporting customers in any needs they have. We were requested by customer to prototype a series of gears. One way of doing it would be to design and manufacture steel mold or aluminum mold and then produce those parts on a small injection molding machine. And that process takes days, sometimes weeks. And any change, any iteration would add to that process even more. Our potential is basically to manufacture or make 3D printed parts like cores and cavities out of the digital ABS using Object 500 Connex 2 3D printer and install it on a small injection molding machine and produce parts within 5 hours. 5 hours is the time to produce parts on a printer, and the parts for customer can be done within a few hours later. Every time we want to change geometry, we change a file, we print it again, and repeat the process until we are perfected. It cuts the time for our prototyping and delivery time for customer.
The Stratasys PolyJet 3D printers are a great complementary addition to the Millicron products. They allow us to take our customers' prototyping process and reduce it from months down to days. I think if you look at the 3D printing process, as it moves forward and becomes faster, as the machines become bigger, it's just going to become more of an integrated part of the injection molding process. So as 3D printers continue to develop and add benefits to those variables, it's just going to be a benefit to our customer base.
Okay, so that should give you a good idea in terms of how this process workflow is happening. And this is a really interesting example of not additiving your product. So you're not doing additive manufacturing for the thing that you're selling, but you're doing additive manufacturing of the tool that helps you make the part that you're ultimately going to sell. And we'll talk about jigs and fixtures and additive manufacturing of tooling later, but that's something that you may have heard in some of your other additive classes, is that sometimes companies, in order to learn about additive manufacturing or in order to de-risk additive manufacturing, they're not necessarily willing to commit to additive manufacture of their exact products that they already know how to make and sell, but they're using additive manufacturing as part of their machine shop or as part of their tool set in order to make the tools that they need to manufacture their products. Also, you'll notice in that video that they called this material that they were making molds out of digital ABS. Now, PolyJet uses photopolymers, and you know that ABS is a thermoplastic. And so what they're doing is that they're selling photopolymer resins with properties that are similar to familiar polymers that people all know. So lots of engineers or lots of people in the plastics industry are familiar with the properties of ABS. Digital ABS is a proprietary UV curable formulation with properties like ABS. But it's not a thermoplastic, so this is not not a thermoplastic like ABS because it has to be UV curable. So, you know, this is not an advertisement for PolyJet machines or Stratasys per se, but this is how they're selling this proprietary process, and some of these proprietary resins is based on the properties or based on familiar properties. And we'll look at this when we talk about stereolithography as well. And so people don't necessarily want to disclose what's in their proprietary resin, but they're trying to sell properties that are like a certain plastic so the engineers can think about how to deploy these different materials for various uses. So that's very interesting. It should give you some idea of what's out there in terms of PolyJet. But like I said, we won't talk too much in detail about materials or about exactly the process because it's still proprietary. There hasn't been lots of research done in this area, but it's very useful for production of parts. So this is just giving you an idea of if you make a metal mold, it's going to take you about 2 months to get it through the machine shop. It's going to be expensive. And if you make a polyjet mold, it's not going to last as long. And so maybe your polyjet mold is only good for 200 parts. And maybe an injection mold is good for 500,000 parts before it has to be refinished. And so if you're going to go into production and you know exactly what your design is going to be and you're ready to do injection molding, perhaps you'll choose the metal mold for its long lifetime. But if you're still in the design phase, this is good for design and proof testing as you're iterating on your component. So this is really interesting because it gives you a way to rapidly do injection molding development without all the machine shop time. Any questions on this?
Yeah, I have a question.
Go ahead.
When you're looking at this and you're using the polyjet mold, now you're going to get different heat transfer within the mold. So is your physical properties going to be different?
So that's a good point. So what Ben brings up is that since this mold is plastic and it's not metal, the cooling that you have in the mold could be different. And, the mold is set at a certain temperature. And so I think that perhaps the cooling will be slower or there'll be more heat inside the part. And so that needs to be designed in terms of low cycle time. Maybe you have to keep the mold closed a longer time to allow the part to cool. But they may put some conductive filler in the polyjet material because you can have some conductivity in these resins. And so I think that would be down to the specifics of what's possible today and what they have experience with. But yeah, the mold will behave a little bit differently than a metal mold will. And that's one of the reasons that it might only be good for, just manufacture of a few parts. The heat transfer is going to be different. Cycle time is going to be longer. Also, the dimensional accuracy is not going to be as good. The mold is going to age, especially if you're injection molding hard polymers into it. And so I think that it's not perfectly the same as a metal-based mold, but it's good enough to do this type of prototyping, especially with small scale parts where the cooling might be reasonable anyway. But
Makes
that's
sense.
a good point.
Cool. Thank you.
That's a good point. When you do industrial scale injection molding of big parts, the cooling channels inside the mold are an important feature of mold design, and that's not necessarily approached in what we saw here. Good. Any other questions? Has anyone used additive manufacturing to make tooling or to make a jig or a fixture rather than additive manufacturing the components? So rather than additive of this gear, so you could easily make this gear using binder jetting, but you might want to have this out of a very specific plastic that the company wants. And so you can't really additive that and get the right properties. But has anyone used additive to make tools or jigs and fixtures like this? All right, well, it's something to think about, especially if your customer or the component that you need has very specific requirements on materials. There's no guarantee that you can meet those material properties, but being able to make a tool with additive to help you manufacture the component is a route that's possible. And a lot of people have been using additive for that. And we'll see other examples of that as class goes on. Any other questions or comments before we move on? All right. So this is a really cool paper. I like this one, and it's not in terms of developing more of the science of PolyJet, but they're comparing different printing platforms between, they have a FDM, they have a PolyJet, I think is B, yep, B is a PolyJet, and then C is an SLA that's made using digital light projection. So A is material extrusion AM, and you can see that because it's got the striations in the parts. So those are the roads that we can see. This is PolyJet, and this is SLA. But you can see now they were just comparing this microfluidic device, and you can see the difference in these parts right from the photographic images that they show. And what's interesting about this is even though PolyJet and SLA are totally different processes, SLA is going to be layers of photopolymer resin that are all polymerized at once, and PolyJet is a material jetting or a droplet-based technique. You get very similar parts from the two. The surface texture is good. Things are looking totally reasonable. Whereas material extrusion AM, of course, you're stuck with the nozzle size, so you can see those artifacts in the part. Now, if we were in class, if you look at a PolyJet part versus an SLA part and look closely, you can, in some cases, tell the difference between the two, because the PolyJet, while they're smooth, sometimes you can see this dotted surface texture right here. You can sort of see it on the remote, or you can see it on the edge of this component right here. It looks like it's made by flattened droplets. And so there's a little bit of, let's say, orange peel, if you're familiar with that, or a little bit of roughness that you can see in some of these PolyJet parts, where SLA parts can get pretty darn smooth, and you can also dial in the surface texture in stereolithography parts, as we'll talk about. So there are some slight differences, and if you're interested in comparing these different platforms, this is a nice paper to take a look at. And so if you look at the microscale of these parts, of course, you can see the roads from your material extrusion AM process, or they called it FDM in this paper. In PolyJet, you can see these flattened, I get it spelled correctly here. Whereas in SLA, you have 2D layers, especially with DLP, since in a DLP type SLA, you expose the whole layer at once. And we'll talk about that in the next couple lectures. But on the microscale, you can get things that look quite different based on the technique. But this is interesting because you can see the surface texture in the macroscopic part. You can take them under the SEM and look to see what's going on and how these components are built up. And of course, you could do the optical profilometry, and so you can get the roughness profile. And what's cool in the PolyJet part, again, these look like droplets that were sort of flattened. You can sort of see, like if you take a ball of silly putty and flatten it with a roller, it kind of looks like this, versus this pixelated structure from the DMD, or digital mirror device, in SLA. So again, this is PolyJet flattened droplets. And what's cool is the DLP is done with something like a computer projector. or one of those old school TV projectors, but it's a bunch of little mirrors that reflects the light, and you can see those pixels on the cross section right here. So you have this pixelated structure in the SLA where you have this flattened droplet structure in the polyjet. And so this will affect your mechanical properties. This will ultimately affect your part performance. And so that's an area of future study. And then you see in the performance of the microfluidic device what this looks like. And so that was the point of the paper. And that's very interesting, looking at the different morphologies of these parts. Any questions on this? Okay, so we're going to switch over to lecture 7.1 that should be on Box. And so let me bring it up here. Oh, I have to go into my archive. Let me find it. Okay, so this should be on Box for you all. And this is 7.1. And we're going to talk in detail about some of the inks. We're going to talk more about inks when we get to stereolithography, but I wanted to compare and contrast a little bit about these polyjet inks versus about inks that are used for binder jetting or the multi-jet fusion or high-speed sintering. And so you notice that we're talking about liquid feedstocks. And so whether we're in a powder bed or whether we're making light reactive photopolymer curing, all out of polymer, so material jetting or polyjet and vat photopolymerization or SLA is all polymer, no powder, whereas powder bed fusion and binder jetting both incorporate a powder bed type of process. And of course, binder jetting uses a liquid to do the powder bed fusion versus selective layer sintering of the material in the powder bed. So anyway, all of these processes that we just discussed rely on liquids and mostly rely on liquid polymers in order to get done what they need to get done. And so we're going to study how to make these liquid polymers and what's in them, especially in the context of stereolithography, because lots of polymer science has gone into making SLA resins. For binder jetting, multi-jet fusion, and material jetting, there's a lot of proprietary knowledge in terms of what goes into that ink formulation. And so there's not as much open information on those sorts of inks, although HP has lots of patents and things like that. They don't want to tell you a lot about that. And so we're going to have less open information that we can discuss for those sorts of inks, but we will go in depth in terms of UV photopolymer resins when we talk about SLA in a lecture or two. So we go back to 3D hubs, and they have a nice binder jetting tutorial. And so we just remind ourselves that, okay, binder jetting is we're putting ink into a powder bed, but we're not fusing that powder bed. So it's not powder bed fusion, but we're using the ink to cause some sticking together of the powder in order to make what's called a green body. So this is different than powder bed fusion, where you're trying to fuse the powder together like you are in multi-jet fusion or high-speed sintering. Binder jetting is its own process. But binder jetting is interesting because it relies on these polymer-based inks in order to do the binding. So if you've ever made a ceramic in the lab, you basically take ceramic powder, you take some sort of binder, that's usually a liquid, you mix it all together, you cast your ceramic form, you do slip casting or tape casting or what have you, and then you sinter that final form. And so what binder jetting is doing is basically we have a powder bed, same as we've discussed before. So this is powder bed. And this is usually metal powder or ceramic powder, although it could be polymer powder if you want. But this binder, this is an ink-based binder that usually has solvent plus polymer. The solvent goes away and the polymer is left to do the binding. And what you end up with is a green body inside of the powder bed. And so you need to get that green body out of there and then sinter it. And so all of these binder jetting parts tend to be sintered, or they're heat treated or consolidated in some ways. What's cool is you can also infiltrate that porous green part after it's debinded and make a composite metal part, and we'll look at that in a second. But these parts right out of the binder jet machine are called green parts because they haven't reached their final form yet. But this green body really relies on having a good binder to stick all the powder together. So does anyone have experience with binder jetting? You can unmute yourself or raise your hand. I know Paula is working on binder jetting because I know who her advisor is, but has anyone else done binder jetting? Great. Okay.
I have not, but an incoming project of mine will be using it.
Yeah. So are you going to be doing binder jetting of sand or ceramics or metal, or to be determined?
I believe it's a polymer-based binder.
Ah, interesting. Great. Yeah. So there's like PolyJet, there's a lot of proprietary information out there, and we'll see some videos here from X1, and we'll look at some of their products. But binder jetting is one of the ways that you can make additively manufactured metals and ceramics without having to do powder bed fusion or some other expensive process. So this is worth looking into, especially if you're going to work in this area or start to design new binders to do what you want. So as they say, the build volumes can be big because this is a simple process, and so we can have large build volumes. And it's cheaper and easier in some ways than some of the other powder bed fusion or material fusion processes as they describe up there. So that's really interesting, and you'll see some big parts that they make using this sort of sand casting or this foundry type process. So let's take a look at this video right here. So this is a binder jetted form that's going to be used for a foundry operation where they're doing casting of aluminum, magnesium, iron, and steel. And I think this one is up, although let me grab it. Oh, let me see if I can grab it. There we go. Okay, sorry for all the YouTube videos today, but it just turns out that that's how it goes. So let's watch this video on binder jetting of foundry forms. This is really interesting, and this is from a company called X1 that does this.
Binder jetting, X1's patented 3D printing technology, is especially designed for industrial application. And perfectly suitable for the continually growing requirements in the foundry industry. With X1's technology, foundries are able to realize highly complex molds in almost no time. From special internal structures to hollow printing, fast, economical, with short development and production times, within hours, instead of weeks and months. Binder jetting. The 3D printing process, binder jetting, got its name from the binder, a glue that is applied by the printhead during the printing process. After the start of the print job, the 3D print happens in two main steps. In the first step, the molding material is applied by the recoater. Layer by layer, the recoater applies molding material on the build area. With high precision, placing two grains the size of a sand grain exactly above each other. In the second step, the printhead applies liquid binder. The high precision printhead allows the binder material to connect every single grain of the molding material completely, grain to grain. These two production steps are repeated. Again and again. And again and again, until the desired object is built layer by layer. After the printing process is completed, the loose molding material is removed. The printed parts can be extracted, and no matter how complex they are, finished during an easy post-process. Binder jetting. X1's 3D binder jetting technology offers new business options for the foundry industry. For individual parts, for small series, and for serial production of complex parts. With innovative production alternatives in many high-growth industries. With ideal material utilization, also for metal printing and ceramic printing. Welcome to X1.
Okay, so a little bit of a dramatic video, but I think you get the idea that you're able to print these complex forms, and they talked about the foundry industry especially. So if you're familiar with investment casting, or if you're familiar with mold-in casting or forging of components like this, you have some mold that you need that has high heat resistance, and oftentimes they use sand for that. So that's very interesting, and you can make pretty big components using this binder jetting process. And so again, there's metal binder jetting as well. And so if you have metal powder, you can do this binder jetting process, and then you can sinter the metal, or you can infiltrate it and get a composite metal part, something that looks like this right here. And so after you do infiltration and sintering, so you have a porous part that you build from the metal powder, and then you infiltrate and sinter, you get reasonable properties, but you see that the binder jetting yield strength is still a lot lower than we would get with selective layer melting or an SLS type process. Again, you have low elongation to break. If you have porosity, and metals are very sensitive in terms of modulus of elasticity if you have any porosity. So you do get some lower part performance with this style of printing. But this issue of how do you build the binder, how do you debind the part, how do you post-process it, those are all really interesting things. And so, again, X1 is a big commercial player in this area, and X1 has a nice website on a few different binders that they use. And we're going to talk about these various binders, except in their metal binders. So this is under the metal materials and binders. They call them different sorts of fusing agents. So whether it's a water-based binder or whether it's a phenolic binder. So phenolic is a type of polymer curing chemistry. Or they sell some proprietary binders that doesn't leave behind carbon residue, which is bad for this type of process. And so in some cases, they don't tell you a lot about what's in the binder that they're going to use for their process. But in other cases, if we go to this website for sand casting, especially, and I think I have the website up right here. So they talk a lot about the versatility of their different binders for different types of sands. And so they have furan-based binders. And so these are based on furfuryl alcohol, which is just a type of polymer. But these binders now will support the sand in whatever shape is of interest. And so based on the chemistry of the sand, whether it's silica sand or some other ceramic, the type of acid or the type of chemistry that you use to do the binding can affect the process. And so they've got furan binders. They have what's called this CHP binder, but this is an ester-cured alkaline phenolic resol binder. So that is a different type of polymer chemistry to do this sand binding. They have these acid-cured phenolic binders, and then they have inorganic binders where there's a reaction between the binder or a reaction that the binder creates between the sand particles. So there's different ways to do this binding, and some of that binder chemistry has been studied. So if you're interested in learning more about binder jetting, whether it's the chemistry of the binder itself, or whether it's the fusion of the particles and the sintering or the debinding, there's lots of interesting steps of the process to get familiar with. But this is how polymers and in some cases composites really influence binder jetting. And so there's a lot of, as soon as this comes up here, sorry, it's hazy, but I think it's gonna pop in a second. But there's a lot of industry knowledge, how to choose the right binder, how to do the debinding. There's lots of different methods out there. Some are in the open literature. Others are proprietary information because there's a lot of industrial interest in this technique. Hold on, let me see if this comes up. Bear with me here. I think it's just a slow internet, and so this will come up in a second. So as we're waiting for the slides to clear here, maybe if I go back. No, let's just wait for a sec. But anyway, this is a nice paper talking about the physics of how to do binder jetting, or the physics of what's going on as you prepare powder as you do the binding, as you cure the green body, as you debind it, and as you sinter the part. So my PowerPoint is thinking, I'll back out of it in a second if it doesn't work. But this paper that hopefully you can see on your notes walks you through each step, walks you through the materials, and then we're going to talk about how the droplets of the binder impact the powder bed and what we might do, there we go, what we might do to formulate different binders in order to make this process work. So this is a nice paper on binder jetting, but we have our powder bed. So what's the powder? What's the chemistry? What's the particle size? All of those things. Our green body is some sort of binder and powder composite. And then we might have to cure that green part. Then we might have to debind it. And in between here, we might have to do infiltration. And then finally, we get a mostly dense part that we're interested in. And this is usually metal or ceramic. All right. And in this paper, they give a really nice review of some different applications, whether it's bioceramics, structural ceramics, or high-end functional ceramics. There's a bunch of references that you should check out in this review. And then they talk about the different powder chemistry. So this is different powders. And we're going to look at different binders, a chart of different binders in a second. But what's interesting now about the powder bed, if you're trying to put binder, inject binder droplet into powder bed. On that X1 video, it looked pretty easy. Well, you just spray some binder on there, you get the shape that you want. That's very interesting, but it's not as straightforward as it looks that you're just printing these things and everything's good. Now, you'd like to have a homogeneous powder bed where you get good infiltration to set up your layer height for the process that you're interested in. So how much binder are you putting in? How does it wet the particles? How does it penetrate the powder bed? But this is happening tens of thousands of times a minute in order to spray down the droplets of binder to hold the powder bed together. And so any defects in the powder bed, so this is a pore or a defect in the powder bed, will cause porosity in the green body. And that's bad, especially if you're not going to do post-infiltration. Porosity in your green body will lead to sintering defects, which will lead to weak parts. And so getting a really nice homogeneous powder bed is important. And you notice this powder bed has a dispersity of powder sizes for good packing. And so by having both large particles and small particles mixed together, you're able to do a lot of volume filling with the powder to get this idea of a homogeneous powder bed. And of course, you know, the morphology of powders is still an area of research, but this is one of the current ideas of how to get a reasonable powder bed set up to do binder jetting into. These are the binders that they talk about in this review article, and they don't go into a lot of the different binder chemistries, but they talk a little bit about whether it's a polymer, whether it's a polyacrylate, or sodium polyacrylate, whether it's a dextrin or starch binder, what some of the additives are, whether they're adding methanol or glycerol or citric acid. And there's a bunch of good references that detail all these different binder chemistries. So again, the formulation of these liquid binders with solvent, with polymer, really depends on exactly what the powder is, depends on the viscosity that you need in order to do the deposition. And so that's why a lot of these proprietary formulations are not well studied, but there's been some academic literature that's looked at this binder jetting system. And so we cover it here just to make you aware that polymers are a part of this process. And what's cool in this paper, and the next one that we'll talk about in the last couple minutes of class, is that they talk about the viscosity getting the right, getting the proper viscosity for binder jetting. And they talk about something called the Weber number and the Reynolds number, depending on the process, and that's defined in the paper if you want to take a look at that. But if your binder is too viscous, you're not going to be able to get effective droplet formation. If the binder is too thin, you get these satellite droplets. So this is a photograph of the droplet that you would like to binder jet. And these are actually 3 droplets coming down. We'll talk about how fast this is in a second. But this is the essence of the inkjet process. So these are all either piezo or thermally driven jetting heads. And so you can look up thermal inkjet versus piezo ejection of droplets if you want. But if you don't formulate your ink correctly, you're going to have these satellite droplets, and that causes issues in terms of getting good fidelity of your printing process. So this is an interesting paper that discusses that, and it discusses what can happen when you get too much sinking, or when you get too much spreading, or you get splashing and breakage of the droplets. And so there's ways to study this droplet formation and how the droplet impacts the powder bed, and then you can connect that to the resulting fidelity of the process. And we'll wrap up today's class by just looking at this cool paper right here. But what they did in this paper was that they used X-ray radiography. And so this is a high-speed technique. Of course, they're using high-speed camera. And what they did was that they looked at binder impacts on the powder bed at very small scale. So we have sort of schematics like this. We've got, well, what does that droplet look like when it hits the bed? But now using this sort of technique, we now have pictures of what the droplets look like as they impact the powder bed. So just to set this up, this is the powder bed. So that's a bunch of loose pack powder. You can see the droplets right here. So this is a droplet. And this is 11 milliseconds. And you see that same droplet 0.05 milliseconds later is down here. And then finally it impacts the powder bed, and you start to see the next droplet come down 40 milliseconds later. So this is next droplet. So this is a high-speed process. You can see how these droplets form and how they're ejected from the print head, which is up here. And this is the powder bed down here. And so this paper is cool because it shows you how messy this process is. You know, on the X1, things were, oh, it's great. We just print this, we get nice smooth parts, but there's a lot of things going on. Hold on, I have a chat here. So if you look in the chat, are parts made via binder jetting susceptible to anisotropic mechanical properties? That's a good question. And the answer often is no, because of the sintering. So because let me go back to a picture right here. So we know that in SLS type parts and SLM, we get good layer adhesion. So we have low anisotropy. Now this is for metals, but we know that's true for polymers as well. For binder jetting, because you're getting binder really sinking in through the layers, you also get good layer adhesion due to sintering. So if you have bad debinding or if you have something going on, even though this part looks like it has some layering on the surface, the mechanical properties will be relatively isotropic because the layers are consolidated really well. Whereas in material extrusion AM, we know you have big layer adhesion issues. And so in general, you have relatively isotropic mechanical properties with this type of process. Does that work?
Yes, thank you very much.
Yeah, sorry, I just saw that. I was looking at the videos and the pictures here, not at the chat. But anyway, to finish this off, and we just have one or two more slides here at the end of class, is that this is a chaotic process. So you can see here in terms of the millisecond timer, they're jetting droplets down as this is going. So the print head is moving in this direction. And you see the powder being ejected from surface of bed due to ink impact. So this is a very small scale, so we don't have a scale bar here, but we do have a scale bar. So this is 500 microns, so this is half a millimeter. So you see that there's lots of things going on as you push this binder or as you print this binder into a powder bed. You also see, you can identify the layer height in this process, which is going to be on the order of about 200 microns. And the last cool thing that I'll point out in this paper, and you're welcome to read this for all the details, is that they're looking at number of ejected particles, and it varies depending on the particle size, the density of the particle, and the binder jetting conditions. And so for this silicon powder, it's not moving around very much. You can see very low ejection of particles, but for alumina, stainless steel, of different sizes, you get lots of ejection of particles. And that's very interesting that this is a chaotic process. This adds to the surface roughness. This also can influence the part quality and the anisotropy if it's not controlled. And so when we see some of these videos, we have to remember that even though at a macro scale, the parts look pretty good, it looks all smooth, a lot of this microscopic video evidence shows us that there's lots of things going on at the part level surface that we need to be aware of. And there's some really interesting powder bed fusion work of metals that was done at Penn State on this exact same type of phenomena. So all these powder bed processes, there's lots of things going on right at the surface. Any questions on this? Any comments that people want to make here at the end of class? All right. Well, thank you very much. Please keep an eye out. I'm going to assign a homework, and I'll give you some feedback on your previous homeworks, and then we'll keep going, heading towards SLA probably on Tuesday. But I just wanted to make sure that we were all on the same page in terms of what these different inks are, what's going on, and we'll talk in detail about photopolymerization chemistry next week. Okay. Thank you very much.
Thank you.
Thank you.